are recording.
Okay, so I think I'll start by providing a bit of an overview and the status of where we're at or where this discussion comes from. We have been tracking the USF work for some time, but in parallel, there was a bit of a discussion going on in the upstream communities and in some mailing lists about information handoff between different firmware components during boot time. And I think that, as Vincent was saying, there's the notion of payload interface in USF, which is not just about the information that's being handed off, but also some aspects related to the system registers and how they're configured. But I think that for this discussion, we'd like to focus on the way the information is encoded and what the information is being handed off between the different components. So as I said, this is a discussion that has been going on within the ARM ecosystem. It's started roughly late last year, and yeah, it's progressed a bit, and I'll share with everyone what the current status is. So in terms of this presentation, I'll start by just providing a brief overview. I'm not entirely sure whether this forum is reasonably aware of the ARM firmware architecture and how the boot flow is generally structured. So I'll just provide a brief overview for everyone's sake to make sure that we all have the same concepts in mind as we discuss the firmware, the information handoff topic. Then I'll present a very early draft of a proposal for what I guess you'd call the data model for the information being exchanged. And it's still to be determined, and we can discuss this further, of what's the actual scheme for the information encoding. I know that in the USF forum, there have been some discussions of using seaborne encoding, and I think we'll touch a bit upon this as well. And I'll just finalize the presentation with questions on aspects that we have related to, in particular, the seaborne encoding and how we can accommodate this. So I also wanted to let everyone know that it's entirely fine for you to ask questions as I'm presenting, and I think that this is meant to be kind of an iterative discussion. That there's no point on waiting for the end of the presentation to ask your questions. Cool. So I'll start just by providing some brief overview of how firmware is architected in the ARM A-profile architecture. We have the notion, or the A-profile architecture has the notion of exception levels and the notion of worlds. These two concepts are to one extent orthogonal, and it's very much like the notion of rings in the Intel architecture, where I'd say, but please correct me if I'm wrong, EL1 or EL2 is generally where the host OS executes, and that's similar to ring 3, I believe, in the Intel architecture. Whereas EL3 and the secure world in the ARM architecture is the counterpart to SMM in Intel. So the normal world, as we're booting up at EL2 in the normal world, will actually run the bootloader. The secure world generally runs at secure EL1, the standalone MM, which is an SMM-like component that's derived from the EDK2 codebase. EL3 is where the runtime supervisory firmware or monitor firmware resides. So the normal world can interact with EL3 at runtime via a set of well-defined interfaces. But generally, and we will see a bit more about this, the normal world firmware doesn't really request any services from the supervisory firmware during the boot time. And I think that's what the FSP concept is on the Intel architecture. So in a nutshell, we don't really have that in the ARM architecture. But But now looking in detail at what the boot flow looks like on ARM, and by the way, this is really just an example boot flow. From a high level, it's the pattern that is deployed on most of the ARM platforms, but by all means, different ARM vendors can adopt slightly different or even entirely different boot flows. But from a very high level, you generally have a board controller, and that's where the boot flow starts from. The board controller here, denoted as the BMC, is the entity that first releases the host, which is here encircled by the dotted line. And once the BMC releases the host into execution, you would first start the execution from what we've termed here the early bootloader. So this is generally either BL2 from the Trusted Firmware project, but it can be many other things. It can be the U-boot SPL or even core boot, I believe. The point is you already have some form of information handed off from the board controller over to the host. We haven't really focused on this information handoff so far. We've been focusing on the handoff within the host. Sorry, I'm using the term host. I wonder whether this is the term that everyone recognizes. We can also use the term application processor.
Yeah, I think host firmware versus device firmware. I think, yeah, that's a reasonable taxonomy. Running on your main big cores versus microcontrollers in your SoC. So yeah, I think host is a reasonable term.
Thanks, Vincent. So in terms of the information being handed off in the hosts, and probably I should provide a bit of background into why we're looking to standardize this. So ARM partners have raised have told us that they have some pain points in maintaining the different code bases that they need to maintain for their platforms. For the information being handed off between those different code bases. The point is that the current status of things is that every platform is going to have their own very specific implementation of information compilation and handing off. So there's the notion, or there's the request for us to come up with a standard way for the information exchange. This is, in our current investigation or in our current design, we're focusing on a very much ARM-specific way of handing off the information for the ARM-specific layers of the firmware. But once we get into the normal world firmware, and once there's a handoff between the L3 runtime, which generally comes from the Trusted Firmware project, over to the normal world, which is generally the EDK2, U-boot, or eventually core boot, we start entering into the domain of the USF spec, right? So any handoff that follows forward from the normal bootloader over to the UEFI implementation or any other payload should actually use USF's payload interface, right? Now the question is whether for the handoffs in the ARM-specific part that plays on in the secure world, the question is whether or not we can use something similar to the payload interfaces, and namely whether we can reuse the same data structures and eventually the same register assignments, right? So yeah, in terms of the information being handed off, what we need to standardize is the data structure itself and which registers we use to pass on the different bits of information. And I guess to some extent also the system register configuration for the relevant system registers when we hand off from one firmware component to the other or between different payloads. So is everything clear? Are there any questions?
So I guess those orange arrows you have today it's both the machine state and then I guess you do potentially a mode transition between them, like your early bootloader to runtime. It's not just it's a calling interface plus the expected machine mode between the left box and the right box. So
yeah, I mean, so most of these transitions are what we call exception returns. Certainly the one between EL3 and the normal world is an exception return. There isn't a whole lot in terms of machine configuration when you do this first EREDs, because, so for instance, the MMUs are controlled per exception level, and in this case, they would be off. So there's a lot of, this normal world firmware would assume that most of the exception level configurations are undetermined, and it will go and start configuring things as they need to be. Right, but there might be some need to define particular values for the for some of the system registers, but we haven't yet looked into that. We're just really focusing on the data structure definition.
And it makes sense. And so, and then the runtime again is what code you provision into trust zone. That is that what the BL31 component is? What lives in trust zone?
Yes. So
okay.
BL30. So by the way, trust zone is not just EL3. It also encompasses secure EL2, secure EL1, and secure EL0. Right.
Okay.
So anything in green is what you'd call trust zone. Sorry, anything in orange, and that's the secure world. BL31 is just the payload or firmware component that runs in the secure world at EL3.
Gotcha.
Right.
And is it optional, or for AArch64 you have to always do something, or is it? Can some vendors omit a BL31, or is it always required for a full boot flow just to make the machine work?
It's not required, right? EL3 as an exception level, it isn't even mandatory for ARMv8, right? And different ARM vendors can have their own, but when the ARM vendor has EL3 in their host processor, they can come up with their own EL3 firmware, right? Trusted firmware isn't really forced upon or mandated at all.
That makes sense. So similar, if an x86 CPU didn't have SMM or it was fused off, it would omit loading that. So if the SoC has that hardware capability, then this is the point in your boot flow that you would initialize it, but it's not always required depending on the SoC vendor. Okay.
Yeah, but we also have some standardization. So the ARM architecture starts with some very wide open generic options and flexibility for SoC partners. But then we add a layer of standardization on top of that to try to narrow down these options to reduce fragmentation and produce more standards-based system design for operating systems and software to depend on. And in the standard-based systems, EL3 is required.
Okay, that's your PSCI and other things, or I don't know the names.
It's in the BSA, base system architecture, requires certain elements of the ARM architecture, and EL3 is required.
Gotcha. Okay, that makes sense.
So, but Vincent, I think that you alluded to a point that I actually wanted to make, which is the platform configuration is mostly done via this flow. Can everyone see my mouse cursor?
Yes, it's on top of EL3 now.
Yeah,
BL2. Yeah.
So the platform configuration is mostly done on the early bootloader and the EL3 runtime components. Once you hand off to the normal world bootloader, platform's already configured. Of course, the normal world bootloader might have some device drivers, for example, to access some flash device that it might need to access. obtain the next payloads. But I don't think that there's really a counterpart to the FSP in the ARM architecture, right? The normal world bootloader in this case, which I guess you'd call the platform orchestration layer, doesn't call into the L3 runtime as it's doing its initialization, right?
I see. So it's sort of fire and forget. Once BL2 and 3 are done, normal world doesn't necessarily call back to the prior two blocks to complete its initialization. It does it all within normal world bootloader.
It does, yes. But there's an interesting aspect on this, and you did mention PSCI. So the OS or the runtime aspects of the UEFI implementation may call into EL3 using interfaces such as PSCI and some others. But it's just that during the boot procedure, in the way that the current normal world bootloaders have been so far implemented, they don't really use any runtime interfaces. So yeah, the OS does use them at runtime, but not the bootloader.
Gotcha. And the BL2 doesn't leave behind, like pass forward a table of function pointers that the bootloader would call back into. It's really BL2 is run to completion, doesn't provide sort of persistent services in memory. It's done and sort of out of the picture from a software model perspective.
BL2 goes immediately out of the picture once it loads and authenticates the L3 runtime, and also I'm omitting from this diagram that there's also an aspect called the secure world payload, which generally is the trusted OS. That's all loaded and authenticated by BL2. And once that's done and you hand off to the next component, then BL2 gets immediately out of the picture. But yeah, so in a nutshell, there are different firmware components. We see a need to standardize the information being handed off between them. Hopefully, we'll be able to reuse and adopt the data structure that's being standardized in the USF
Gotcha.
in the USF forum.
Makes sense. And I guess DRAM initialization, like DRAM that stays at a fixed memory addressing location in your address space, is that done in BL2, or do folks do it in their bootloader? Or I'm guessing it has to be done probably before the EL3 load, because that code persists forever in DRAM.
So I think that's a part of the boot flow which is a bit more diverse across different platforms, right? I think that even in some platforms that can be performed by a separate processing entity, but the more common approach is for there to be some early ROM code that executes in the host, which then does the DRAM training executing off of SRAM. But yeah, so I wouldn't really be able to tell you whether
Gotcha.
there's...
Yeah, I guess it only probably really matters that if these tables are associated with the arrows, the tables may have to move if memory locations move, or by the time you get to green, you have a known address space mapping. So, but yeah, that it's. I only was asking is, does it read on the software model? But it sounds like it's.
There are some constraints. There are some constraints for the firmware for the way we design the handoff data structure. So things are way simpler as you move towards the green arrow. But when you're in a more constrained execution environment, things are trickier, right? And so I think we'll touch upon that in terms of the CBORD encoding, whether you can really support it from very constrained execution environments, such as this early bootloader in some designs.
Gotcha. Okay.
So I think that by now everyone has a decent picture of what the firmware, what the boot architecture is on the ARM architecture. So I just wanted to start giving everyone a bit of a background on the discussion that we had late last year. As I said, the different upstream communities asked us to come up with a standard data structure. And I think that we've been focusing on the data model, taking for granted that the information would be encoded in what I will call a plain encoding, which is really just using using native data types from the processor and defining a set of nodes as a set of fields at a very well-defined offset from the start of the node and of a well-defined size. And also the NDNS is specified when we're defining these nodes in the spec, which is, by the way, it's still just a draft proposal. It's publicly accessible. The spec, as I said, has a sequence of nodes defined. And hopefully this is enough, or at least is a path forward for the standard for the standardized information exchange. So this, I mean, by the way, this is very much similar to how the HOB list was defined in the PI spec. I assume that most of the people in the call are familiar with the HOB list. I think that at least, in fact, the USF defines the public USF documentation defines the HOB list as the preferred data model for the payload interfaces. But when we were having this discussion with the different upstream communities, we were told that there were some drawbacks of adopting HOB list, which was our initial proposal. The thing with the HOB list is that some parties in that discussion weren't really comfortable with using with-it HOBs if they had to use bespoke nodes. So they prefer not to be forced to use with-it or HOBs, and they also wanted to have the ability to have nodes larger than 64K, which is one of the constraints with the current HOB list definition. Right. So we were asked to come up with a solution where the nodes are identified by a tag ID, and that allows larger than 64K payloads. So in our initial proposed solution, we came up with a design where you have a node header, which is very much like the HOB list again, and you have the node payload, which is defined by the tag ID in the node header, and this can be arbitrary in size depending on how the node is defined, but can be larger than 64K. So the HOB list, or the handoff list, as it's defined, will start with a list header that determines the version of all the nodes contained in the list. Following the list header, there's going to be a set of consecutive nodes, and that's pretty much how you that's pretty much the data model. And the nodes are going to be present in an upstream repository, but I think I'll talk about that in the next slide. I think that for now I'll just make a pause and ask whether there are any questions, and whether you consider this as a feasible approach for the payload interface. Keeping in mind that we will still discuss whether or not we should go with plain encoding or whether we can adopt seaborne encoding.
So little Indian, you don't have any, there's no folks who do big Indian anymore, so that seems pretty reasonable. And then everything's well typed. There's no natural sized integers, so it's invariant of 64-bit or 32-bit, correct?
Yeah, it is,
okay.
yes.
Okay. Makes sense. And obviously people love GUIDs because namespace management, you can define your own. So I'm guessing you'll probably have quote OEM reserved versus standard defined.
Yeah.
That was always what GUIDs got us, but yeah, I can imagine the complexity of compare GUID and the ROM bloat carrying GUIDs around. So I can understand the feedback you received about GUID. So
Yeah, but going a bit further there, the issues with GUIDs is that apparently if you look at the data dump, the GUIDs are just very difficult to
horrendous for
parse.
debug. Yeah.
And also people are worried that sometimes there's NDNS mismatch when you're interpreting, which is wrong, as the GUID is very well defined in terms of NDNS, right? But apparently sometimes from people's experiences that sometimes you still have mismatches between the producer and the consumer.
That makes sense. No, I mean, optimizing for the debug experience, given that's where a lot of the business workflows are, makes sense. That pushback, I can see that perspective. Okay.
Right, but as you were hinting at, Vincent, yes, we did segment the tag ID space. So the tag ID space, the first chunk is for the standard range, and I think that we have roughly 1 million tag IDs here. All of the nodes, and by the way, I think I've mentioned this in the beginning, the nodes are all going to be defined in some repository. So whenever communities want to request a new node layout, they would just issue a pull request, which would then probably be reviewed by a set of maintainers. But this is really your only way to get a new node's ID and layout. So on the standard range, that is, right? Because then we have the OEM range that has 64K tag IDs. These are very much ImpDef. So your device manufacturer or your firmware provider can come up with bespoke node layouts, and as long as it uses the OEM range, that's entirely fine. The firmware provider needs to take care of the collisions, but that's up to him, right? I think that it's still TBD whether we need to have other segments to accommodate no definitions of other entities involved in the device manufacturing, right? Whether we need a range for the silicon provider and that sort of stuff, right? But for now, it's just allocated the OEM range. And I think that this is very similar to the current concepts that already exist, certainly in the U-Boots code base, but I assume also in the core boots code base as well, in the core boot tables. So in the first draft proposal that we currently have publicly, we've introduced 4 types of nodes. The first one is the empty node, just because we want to allow information to be scrubbed off of the list without requiring all the previous nodes to be moved around. The remaining 3, the first one is the FTT, which holds the hardware description. I think that this is a widely used pattern in the ARM ecosystem. I'm not entirely sure whether this is as common in x86. It's also adopted in the U-Boot codebase for x86, I assume. We have legacy support for the hops, just because when the normal world is EDK2, you really want to, or ARM partners want to be able to pass a hop list from EL3 over to EDK2 in the normal world. And the last node that we've defined so far is the ACPI table. The main use case that we have for it is to carry over the TPM log, either by using a TCPA or TPM2 table. But of course, this set of standard nodes is limited, perhaps. So the expectation is that the communities would use the pull request mechanism early on, and as time goes by, eventually the list of nodes is going to be more complete.
So I see you have a way to convey things from the different existing sort of handoff mechanisms. But say you wanted to build a payload that was maximally interoperable with core boot, U-Boot, EDK2 style firmware, slim bootloader. Would you find yourself having to parse all the formats because you don't know what the platform code provides? Or if platform code wanted to be maximally interoperable, would it provide all of them? How do you imagine people fabricating their use of these various encodings? Would they build a payload on the right, hand in glove with platform code, and elect to use one of them, or do all for maximal interoperability? What were you, did you have any thinking, or maybe I'm misinterpreting what this flexibility buys?
So, sorry, are you talking about the information encoding or the node types?
The node types.
Right. I mean, there's some notion that at device design time, there's some agreement on the different node types that are going to be passed along over the boot path, right?
Okay.
The standardization effort is really just to allow the different code bases and the people that need to invest resources in updating it and maintaining it to have a widely adopted ecosystem accepted way of exchanging information, right? So I guess that we need to accommodate the different types of information that people are exchanging, but certainly some platforms won't really have all or won't use all of the node types, right? It might be that some platforms just use hops. Some of them might focus a bit more on the FTT. Yeah.
So you're not thinking of it as like a universal transport where, hey, to use any payload, provide them all, and
No.
Okay, because that seems like a combinatorial explosion potentially of complexity. Okay. I see where you're going.
Yeah, I think that we're trying to provide people with tools to do their job and hopefully making their jobs easier.
Got it.
Yeah, so the node type discussion, I think, is slightly different from how we encode the information. And by encode information, I think is we start from the data model and then we decide whether we should really store the different fields as 4-byte integers directly, or whether we should encode it in some other using some other information encoding scheme. And I did quickly glance over the different discussions that are going on in the USF forum in groups.io. I assume that everyone that is in this call has access to, and I'm also assuming that that information is not privileged in any way, right?
Yep, it's all world readable, Creative Commons. Yeah, it's all just out there. Yeah, should be part of the potential discourse. Yeah, there's no company specific copyrights or anything. It's just.
Oh, and yes, by the way, I entirely forgot to mention this. As we've started creating this draft proposal for the data model, it does have an ARM-specific license, but that's just because it was the easiest path forward to make this document public. I think that the intent is, and especially once we start placing the nodes in a Git repo, is for us to have a Creative Commons license on all of this. So. And the idea is really to take down all impediments for this to be widely adopted eventually, if that makes sense. So, but in terms of data encoding, I've already mentioned that we have the plain encoding, which is the one that we usually deploy in our firmware stacks. And you can refer to it as probably regular C data structures that are packed, right? But this plain encoding is really just about using the natural processor types. And the definite benefits of this is that you don't really have any overheads to read or write. Those are you just get the fields by issuing a load or store in your low-level instruction set, that things are simpler to debug. If you look at the data dump, you can. It's humanly readable what the information is stored there when we're using plain encoding. It's also less demanding for low memory environments because you don't really have, or you don't require the CBOR parser or the encoder and decoder. And I also have, and by the way, this is a personal opinion, so I may be entirely wrong, that it's easier for us to push the adoption of the plain encoding. It's just because the different code bases are already using this, although the data model is not standardized, or it's a de facto standard within the code base, but they really just using plain encoding just because that's the simplest thing to do. And yeah, but again, I may be wrong, and there might be compelling use cases for CBOR encoding. I guess that one of the properties that we were aiming at with CBOR encoding is that it's self-describing. It's also removes the issues of getting NDNS to match between producer and consumer, right? Other comments I've heard or positive points with respect to CBOR encoding is that there's widely available tooling. So we wouldn't really need to reinvent any tools. And also there are libraries, a lot of libraries actually available upstream. So again, as I said, it makes it much easier for information to be exchanged between different processing entities. I think that in the beginning I mentioned that there's an exchange between the PMC and the early stage bootloader, but I guess that there are other examples of information exchange between the host SOC and different processing entities. I think that in USF, you mentioned about XPUs and DPUs, I believe, and certainly that won't be an Intel specific design. So might also make sense on the ARM deployments. So I guess that there's definitely there's definitely pull for CBOR encoding. On the downside, if you look at the memory dump of information encoded with CBOR, it's going just to look obfuscated to a human. So there's this additional hurdle. But I think that what we wanted to discuss, given that there are positive points on both encodings, the question is whether we can have both encodings being supported for the payload interfaces, and what does everyone think about this? Is this feasible? Is it even worth considering? Or is there some sort of consensus that we need to choose one over the other?
Yeah, I think that's the challenge, is if we have too many options, it's what do the psychologists call the paradox of choice. You know, we don't get the synergy and community all rallying behind one approach. But then the flip side is if this approach is too complicated, and again, we talked earlier about, you know, a lot of people have to do direct memory peaks, bringing up hardware. If this is an inscrutable memory format, that's a downside. So yeah, depending on which side of the lectern I was on, I could argue, I guess, either. So maybe I'll pause for other perspective. Maybe Kuo, Nico, Shang. Yeah,
Yeah, for the first one, basically it is very similar with cobbled table, right? And also very similar with hop list. I didn't see much difference. And for the CBOR, yeah, now we are it is under discussion. We're trying to use the CBOR if the for example, the community agree to use a self-describing structure. That's the one we think is acceptable. Using Siebel, both the bootloader and the payload needed to do encoding and decoding. It adds some more overhead. But as we all agree to use same format, I think from USF viewpoint, it is good to have a common one, not that's okay. So I'm not sure we can support both. From memory dump, from the Siebel, it should not be very difficult even to a human because they are using string and the value. The Siebel format is not difficult also. The potential is led to the structure to be readable to the human. So the third one, I'm not sure it is true. Previously, Tandun did a POC. We can double check that one. That is also, Siebel should be very also straightforward. It is just a string value for the most of the case. Yeah.
Yeah, but I think that, and I might have a skewed perception here. I think that there are two different, let's call it levels of abstraction. I think that there's the data model and how we structure the nodes and which fields they have. And deep down, there's how we represent these collections of fields in memory. And the only thing I was wondering is whether the plain encoding and CBORD can be used, can be adopted for as different encodings of the same data model, and whether that would ease the adoption. So, for instance, how have the CBORD encoding discussions progressed with some communities such as you? But I'm not entirely saying that that's going to be a tough discussion or that there's going to be pushback, but I'd assume that more embedded or mobile focused communities might not see as easily the benefits of CBORD encoding that brings you the simplified interoperability between different processing entities, right? I do appreciate the fact that giving people more flexibility may make it harder for there to be cohesion. But yeah, I think that there are the two. You can see this from two angles, right? Sometimes providing the some more flexibility will maximize cohesion because it makes it easier for things to be adopted as a concept.
Yeah, no, it's a good point. And then if maybe then the trend line will elect one of them in practice to predominate, but we don't try to predict as a thought experiment which is better. So yeah, leave the options, and then maybe the community practice rallies behind one or the other. Yeah, I mean that's definitely an approach that respects the different choices some of the upstreams may choose with this infrastructure. Since we're not trying to build the universal socket here where we have to publish all the formats and all the encodings. We're saying, hey, kconfig this one or that one, or PCD this one or that one. As you build your firmware, having more options is good, and then maybe the practice over time will elect one over the other. Yeah, that's a good point on the cohesion you mentioned. Not trying to predict the future, but allow allow for the different options and don't mandate one or the other, but put the tooling out there, the infrastructure code, and as we vet this, have a few platforms that demonstrate all of the modalities, so it passes the physics test. Right? It's actually implementable.
Yeah, I think the SIBO also supported the array, also supported the binary. I mean, at last we agree to use the SIBO, for example, the literally for different information you pass to payload. Yeah, that can be, you can select using a binary or using arrow or using the simply string value like that. Yeah, looks the first one can be a payload of the SIBO. Otherwise, we all agree for that. Yeah, kind of. Yeah.
So I just also wanted to understand with this forum whether we do see a need for the different nodes to be defined somewhere, right? They wouldn't just be encoded in CBOR and consumed as is from the firmware that consumes the CBOR encoded nodes, right? There would be a notion of node types that's publicly available to all the firmware developers, right? Is this correct?
Yeah, because to get the interoperability, you're right. The wrapper transport is just the one dimension, but the semantics, what are the node types? I think we'd want to enjoin. So, and look at sort of the initial USF proposal with the Hobbs it elected as just a straw man to start that conversation. But correct, it's both the encoding and the data model. Yeah. I think we'd want to have some alignment potentially on both. And I guess you were thinking on the data model. Was it?
Yeah, we were focusing on the data model because we weren't really spending a lot of cycles on trying to figure out the encoding itself. We were assuming that we would just go with the plain encoding. But yeah, I mean, definitely thinking about the data model and getting the one which is which makes it easier or that makes life easier for some of the use cases, then it's definitely worth accommodating that. And as we said, our current hope is that we would be able to support both plain encoding and CBOR encoding. But it's definitely something that we can continue on discussing. We don't really need to commit, obviously, to a decision in this call. So
yeah,
in terms of...
I agree. This is more informational sharing. Even this first tranche of USF meetings, including next meetings, FSP, are more informational. So yeah, this is just get the conversation started. But yeah, we don't have to click the yes or no button today. I agree. It's not a decision meeting. Yeah.
So I did go over some of the material in the groups.io, and I did think I did see some study on what's the overhead of CBOR encoding in terms of how much does the encoder and decoder take in terms of memory in the image binary. But I was wondering whether we've done some study on what's the time overhead, so to speak, to decode and encode data, whether that's significant or perhaps negligible. And I was looking at roughly order of magnitude values. It's entirely fine if that study hasn't been made.
Yeah, I don't think we've done that responsiveness. That's a good question, and we can follow up on it.
Yeah, last time Tandwin did a POC only have the size overhead data. We didn't really collect the time impact. Since it happens in the memory, I would assume, it will not take too much time.
But in terms of binary footprint, I think it was roughly 1 kilobyte. I think correct?
Yes.
Okay. Yeah, so the second open question, by all means, this isn't really an exhaustive list of open questions, but the one I was thinking about, and this ties in with the previous question of whether or not we can support the two encodings. And if the hypothetical answer to this is that yes, we can support the two encodings, then the follow-up question is whether or not a handoff list can have nodes that have different encodings, or whether each list, as it's being handed off from one payload to the next, would it need to have all nodes of the same encoding? And again, I think that we've already established that the precursor question isn't going to be answered today, so I don't really expect this one to be answered either. So,
from CBOR, I mean, definition, it can support this thing, but eventually, since it needs the payload to consume it, need the bootloader to produce it, the data. As long as, I mean, bootloader and payload agree to use the same, data, it is possible from my viewpoint. But if you, embedded a very, very long structure, right? Very complicated. It would be very difficult to, have both bootloader and the payload to adopt it. So it depends, for the what it would be in this, embedded in the CBOR.
Okay. Okay, I think we're quickly running out of time for this meeting. I don't really have any additional material to present.
Well, thanks for putting this together and getting the conversation going. And again, it's great to hear that you've already engaged with U-Boot, I think Core Boot, Slim Bootloader, U-Boot, EDK2. We want to sort of find the Goldilocks, if there's a Goldilocks solution among all these community-based bootloaders. So yeah, that, and then the ARM, the scaling experience you've had to date, I think are definitely valuable. And yeah, we can keep following up on the mailing list, and then I do believe that we should click into the aligning data models also if possible. So
yes,
hopefully it's the beginning of a class of conversations we can have here and then in the other bootloader communities. So thanks for putting this together, and Mickey, for our cruise director, setting up some Europe-friendly meetings. I think some folks in Germany are probably happy, like Shang, who was very, very brave and valuable, but it's you don't make friends by making folks wake up at 2 a.m. their local time. So
yes.
Thanks for doing that.
Well, I'm going to stop recording now. And is there anything else anybody has to wants to bring up?